Hello, good afternoon. It's great to be here, and I'm gonna talk to you about Mega, but I don't think we need the microphone, right? Are you hearing me? Okay. Do you want me to turn on? Yeah, for the recording, right? So I'd like to thank the organizers, and it's great to be here. And I'm going to talk to you about the Bootstrap test and the presenting trees in Mega. So I'm going to start talking about parsimony method. Parsimony is a philosophical principle that was first put forward by William of Ockham. Ockham is a British city. So William lived in that city, and he was a theologist that lived in the 14th century. And he came up with this philosophical principle that we use today, basically on the parsimony method, that says that entities should not be multiplied beyond necessity. So this is a kind of economy principle. So we should not use more explanation than the ones we need to explain something. So this is the basics of the maximum parsimony method to build trees. So in the case of phylogenies, trees with the least number of substitution that explain your alignment should be the one selected. What do I mean by that? I mean that the trees that need the least amount of mutations or substitutions to explain well your alignment will be the best tree according to the parsimony principle. So first, what parsimony does, the method of maximum parsimony, it sets aside the informative side for parsimony. So unlike other methods, parsimony, maximum parsimony only works with parsimony informative sites. Which are those? They divide the diversity into at least two types and with at least two sequences for each type. So let us look at this alignment here. So we have the OTUs 1, 2, 3, and 4, and we have 10 sites in our alignment. So the first site, site number 1, only has T for all OTUs, all species here. So that means that the least number of substitution to perfectly explain this site is 0, because it doesn't require any changes, as all the species have the same type, which is T. So all the trees, all the possible trees will explain this site with the same number of mutations or substitutions. That means that this site is not informative for parsimony. Okay, this one, site number 2, also is not informative because all the possible trees would require 2 substitutions. Site number 3, however, it's informative for parsimony. So is site number 6 and the site number 8. Why is that? Because the site number 3 divides diversity into 2 types, which are the A type and the C type. Each one of those types have 2 sequences in them. So this is what the definition of a parsimony informative site. And the same goes for the site number 6. It divides diversity into 2 types, type number T, type T, and type A, with 2 sequences on each type. And the same goes for the site 8 also, T's and G's with each type 2 sequences. So for 4 sequences, we only have this possibility, dividing diversity into 2 types with 2 sequences on each type. With more species, we have more possibilities. Here, for instance, I put all possible trees with 4 species. So I have a tree number 1, which joins 1 and 2. Notice that this tree that joins 1 and 2 also joins 3 and 4 together. All right, so you have 3 possibilities: 1 and 2, 1 and 3, and 1 and 4. So these 3 trees are all the possible trees that we can reconstruct with 4 different sequences, are all of them. And the maximum parsimony method uses this. It will reconstruct all the possible trees and select the tree with the least amount of required substitutions. So let's take, for instance, site number 3, in which we require here OTU, or species number 1 and number 2, have the same pattern, which is A. So that means that the tree in which 1 and 2 are linked together here would require a single change. Whereas those trees that have 1 and 2 separate, as they have the same A pattern, they will require 2 changes. Okay, so for the site 8, it's the same pattern, because site 3 and site 8 have the same pattern for species 1 and 2. Here in the site 3, I have A's for 1 and 2, and in the site 8, I have T's for 1 and 2. That means it requires exactly the same tree, requires exactly the same number of changes. Okay, so for site 3, the best parsimony, the most parsimony tree is tree number 1. For site 6, however, it's tree number 2, because 1 and 3 have the same pattern. So it requires the least amount of changes. Like here, see, 1 and 3, the same pattern. So the tree that joins these 2 together requires the least amount of changes. So we do this for all parsimony informative sites in our alignment, and sum the total amount of changes for all sites and select the tree that requires the minimum number of changes. So the most economical tree for parsimony wise. So this is the tree number 1, which would require 4 changes. Tree number 2 requires 5, and tree number 3 requires 6 changes. Would be the worst in a parsimony criterion. So we can search for the maximum parsimony in Mega in 2 ways. First is the branch and bound search. This guarantees to find all the maximum parsimony trees. So we call Mega has a very smart algorithm for the search of the branch and bound search. That means that it doesn't have to reconstruct all the trees. It reconstructs a single tree and it measures the number of substitutions to explain perfectly the alignment based on that tree. So for instance, this first tree, it has a length, we call a length, the number of required substitutions of 964. So, and Mega starts adding OTUs or species to a very basic 3 OTUs or 3 species tree. And if this one is higher, see, this one has a length which is already higher than this complete tree. So that means that it doesn't go further that road. That means that this tree will certainly not be less than this. Will require more steps to keep adding OTUs into that. That means that Mega saves this path and doesn't go further. So the branch and bound algorithm is the time consumed, computer time is optimized. So it only goes further, like this one, see, in which the length is smaller than the one that we had before, a previously complete tree. So it goes further this way, adding more species to this tree, and not to this because this is larger, and not to this because this is also larger. However, so for 4 species, we have 3 possible trees. Here, join A and B, A and C, and A and D. So if I have 5 species, what I need is, I could place the 5th species into 5 different branches. I could place it here, 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 or here. So that means that since I have 3 trees with 5 different possibilities for the 5th species, for 5 species, I'll have 15 possible trees. The same logic goes for 6 and 7 and 8 trees. And actually, this number of trees increases very fast with the number of taxa or species. So to get an idea, for only 10 taxa, which would be much less than the average phylogenetic tree that we have in most phylogenetic studies, for only 10 taxa, we have over 2 million possible trees. So that means that sometimes the branch and bound method that guarantees to find all the maximum parsimony trees is not fast enough. It just takes so much computer time, so long, that, well, we just can't wait that long. And for this, we have a heuristic search for the maximum parsimony tree in Mega. So it starts with initial trees. The same idea goes. It reconstructs an initial tree of, it depends on the algorithms for different programs. But in Mega, it reconstructs random initial trees. So for instance, the default in Mega, I think it's 10 different initial trees. So it reconstructs one and then tries to find the maximum parsimony more or less the same way the branch and bound method goes, but it cuts more paths than the branch and bound. It doesn't only cut those that we know it's gonna be higher, but it cuts those that we are pretty sure it's gonna be higher. Okay, so it cuts more, requiring less computer time. And so it usually finds the maximum parsimony tree, but it's not guaranteed to find the maximum parsimony tree, this algorithm. So in Mega, we have, this is the window for the maximum parsimony analysis. So here you can do a phylogenetic test. You can use this nucleotide or amino acid data. We can use different types of gap and missing. We can select whether we want to use all codon positions and the non-coding sites and the tree search options. For instance, here the same goes, use all sites or complete deletion. The complete deletion would be if you have one species with a gap, it removes the entire alignment column for that position. And the partial deletion is somewhere between using all sites and the complete deletion. Here is the tree search method. So subtree pruning and regrafting and tree bisection and reconnection are different ways of branch swapping the tree. That means that you construct a tree, you estimate the length, and you cut that tree in half and then assemble it differently and measure the branch length, the tree length. And then if it's smaller, then you continue doing that way. If it's higher, you go back to where it was and then start doing some other branching. So these two with the TBR, the first three are heuristic. That means that they don't guarantee to find the maximum parsimony tree, but they usually do. And with the first one being the fastest and the least exhaustive. The second one is more exhaustive, and the min heuristic, it's something that it's originally from Mega. Was an algorithm developed by Dr. Kumar. And this is the mini heuristic and the mini branch and bound. Remember that only this guarantees to find all the maximum parsimony trees. Because why do I say all the maximum parsimony trees? Because since it's a sum of all the required substitutions for each possible tree, the trees may tie. Okay, the best trees are actually 3 trees because they have the same minimum number of substitutions for these 3 trees. Okay, so this is the only one that guarantees to find all the maximum parsimony trees. But it usually requires a lot of time, particularly for more than 15 sequences. It's usually not feasible. So you should use something heuristic search. So this would be the maximum parsimony tree. And Mega automatically generates a caption, which is manuscript ready caption, and the references to the method you use to do it. So we're gonna talk a lot about this, the menus. Now, for instance, the file menu. So here we're starting on this menu here on top of the tree. So the file menu allows you to save and export the analysis summary. Note that if you save the current tree session, it doesn't not only save the image, but it saves the entire analysis so that you can run more analysis to it. All right, but you can save only the image also here, save as image file. In the second menu, the image menu. And here, the caption menu that you can copy to clipboard, and you can zoom in, zoom out, show in a new window, etc. So these are the menus on top of the tree here. One thing that you want to do is also to root the tree. The midpoint routing is the default for distance methods. And the midpoint routing is the root of the tree is placed in the midpoint of the 2 most distant taxa. So this is the default that appears in Mega, but you may say, okay, no, this is wrong, because the midpoint routing kind of assumes the molecular clock to be working. That means that it assumes that sequences are evolving in a clockwise fashion, and you say, no, this is no good, because I know that this species is the outgroup. And what is the outgroup? Outgroup is the species that diverged first, because the biological information in a tree is the relative date or time of speciation, right? So it's important, or it's fundamental that you have a time frame, and this is given to you particularly by an outgroup. So an outgroup is a species that you know diverged before all the other divergences in your tree. So for instance, if I'm going to do a tree with placental mammals, I would use a marsupial for an outgroup. And if I'm gonna do a tree with birds, I would use a crocodile or maybe a snake or another reptile. So you place the mouse cursor on the branch. You know it's the outgroup, and you click on the root tree on selected branch button, and then your tree is rooted where you want. Okay, so it transforms this tree to this tree. Note that the topological and the topological information of these two trees are different. They're not the same. So you can also change the shape of the tree, and for this is the regular, the default, the rectangular shape, and this is the straight shape, curved, and these are okay, but the ones that we most used are the default rectangular and the circular shape. When you have a lot of sequences, a lot of data to show, then you may want to color code your sequences because you want the big pattern, and then you can sum up a lot of information, tree information, into a single phylogenetic tree with this kind of tree shape. You can swap the selected subtree. That means that you're going to place on this branch the cursor, the mouse cursor on this branch, and then you press on the button, and it's gonna turn like this. See, it's gonna flip Nigra down here, and this clade will be exactly as it was. See, affinidisjuncta and heteroneura and Adjustula and Mimica are on the same order as here. So it only swaps this branch with this branch. Why would you want to do this? Because if you want to present two or more trees in your paper, you should swap them so that they would be as close and as similar as they can be, so that only the difference, topological difference, will be shown. So this is the swapping that swaps only the two lineages, and this is the flipping branches, which is a different button, and you also place it here. You see that this provides a mirror image. It's different from the flipping, from the swapping branches, because see here, Nigra and Affinidisjuncta are close, and here they are. So the flipping provides a mirror image of the branch. In Mega, you can also provide the name of the taxa groups using this tool. So you select the interior branch that you want to name, and you can provide them. You can provide subgroups and larger groups that include the other groups. This is very useful if you want to include more information into your tree, so that the user may see more than just the taxon names. But you can put here taxonomic groups, or maybe some feature, some biological information on reproduction or on environment, or anything you want. So Mega also provides you options for rectangular tree, so as taxon separation, branch length, and tree width, You can all set these all according to your choice. And also for the circle tree, so the start angle, the radius, and the center hole, it also set by the user. And the scale, not for parsimony trees that don't have scale, but for other types of tree, you can set the scale also. And you can do a lot of things with labels. For instance, here, this is the menu for the labels, and you can change the font for the taxon labels, and you can display markers. For instance, here I set a marker for the subgenus Sophophora here. So I have this marker and this one for Drosophila, Hawaiian Drosophila. So it will appear on the tree. So you can color code and you can place this in the caption. In the parsimony analysis, Mega also using this button, you may also see the ancestral reconstruction states that Barry was talking about yesterday. But this is a simpler method, and you can just press here, and this is the ancestral reconstruction for all the ancestral nodes, states reconstruction for all the ancestral nodes for site number 1. And then you press on these arrows and you have different sites. So this is site number 1, and this is 2 and 3 and 4. So you can press on this, and then you go through all the sequence and checking out the ancestral state for sites. So it was not the case with the Drosophila, but if your tree, if your file, your data will yield more than a single phylogenetic tree, such as this one. This one is the D-loop vigilant, also from the Mega examples. It yields 4 most parsimony trees, most parsimonious trees. So that means that these 3 are tied up on requiring the least amount of substitutions to explain the alignment. So Mega allows you to see, to check out each tree separately here. So if you press on these arrows, you're gonna see tree number 1, number 2, number 3, and this. You can also compute the consensus tree, which would be like a summarizing tree. And this value would approximately tell you how much polythomies you wanna see on your final tree. So this is the cutoff value for the consensus tree. So this summarizes all the maximum parsimony trees into a single tree here. So you can select the compressed subtree by using this button here. So that means this is useful if you want to if you're interested in, for instance, the relationship, phylogenetic relationships of genera of a family, but you want to be careful and you want to make sure that all the genera are monophyletic before you do your final and most important analysis. So you may want to use a lot of species or some species of each genus, but this is not really what matters most. So you put them all on the tree, and then you compress all the genera into a single lineage here, so that you might be able to fit your entire tree in a smaller figure. So So for instance, let's say that I'm not really worried about the relationships within this part of my tree. So I'll just compress it, and I'll just place Hawaiian Drosophila here. It will replace it with the entire tree, so it fits better. So I can also display subtrees separately, so it is just gonna cut off this part of the tree if I use this button here, like this. And I'm gonna talk about the bootstrap test now. If we have an alignment, for instance, with 15 different alignment columns here and 4 different species, and I'm gonna do a phylogenetic analysis using this alignment, and let's say that I have this phylogenetic tree as a result. So this is my original sequence alignment. This is my data, my raw data, my original data, and this is the original alignment tree. What the bootstrap test does is generates replicates of my original alignment, and this is done with replacement, so that in each replicate of my bootstrap, some columns of the original alignment may be repeated and other columns may be removed, so that I have a slightly different alignment from my original alignment. And I'm gonna build a replicate tree for each replicate alignment. So what does it do? It estimates the internal consistency of my original alignment. Because if I change a little bit my data and I have an entirely different tree, then I shouldn't trust my original data for starters. Because, you know, if I remove a few columns or repeat another, and my tree is very different from the original tree, then I shouldn't be trusting it. And the bootstrap number here is the number of replicate trees that have the same this aus and bus joined in a clade. Okay, so we can do this. So it resamples alignment columns with replacement, so that in a given replicate, some columns will be repeated and others will be removed. So the question is, will replicate trees be consistent with the original tree? And Mega does this, provides 2 different types of results. So you can use this, we'll do it with the parsimony, but maximum likelihood, neighbor join, minimal evolution, and UPGMA all have bootstrap options with them. And if I select the bootstrap method here, it will open up a number of bootstrap replicates, which are, I mean, the higher the number of replicates, the more reliable the bootstrap number is. But it takes time, because in Mega, all bootstrap replicates are exactly the same, have exactly the same algorithm as the first, as the original, in this case, maximum parsimony trees. And this it's not always true for other programs. So in Mega, that means that it will take like 500 times more than a single parsimony tree. So that means, so Mega provides the results for the original tree, which is the tree that was built with your entire original alignment. Okay, and this number means that in 98% of my replicates, Drosophila melanogaster and Pseudoobscura were together in the replicate trees. Means that in all trees, Albovitata and Crassifemur were tied together in all replicate trees. So you can use this as an original tree, and you can also, Mega also provides you with the Bootstrap consensus tree, which forgets about the original tree and just builds a consensus out of all the replicate trees. Just like summarize all the replicate trees. And you can use tree cutoff options in Mega. So for instance, here I just placed a cutoff value for the condensed tree and at 80%. And that means that all the branches that had, let me show you here, numbers, bootstrap proportions of less than 80% will collapse. That means that you're not going to see the resolution here for that branch. So this is 51 is the only one, the only branch that will collapse. Here it is. So this is also useful because you want to focus your analysis and discussion on those branches that have higher consistency, higher bootstrap values. And Mega also allows you to display several things on branches. Of course, the statistical frequency that we just observed, like the Bootstrap and other tests for neighbor join, for instance, it has the interior branch test. So you can display and use different fonts, and even lets you set the distance from the node. You can also display on the branches the branch length, and you can also display the divergence times on the branches. So thank you for listening, and I'll take any questions.
Okay, cool, thank you.